Okay, this is AP review quiz number 1. It's a multiple choice quiz. This is video 3, and we'll be going over problems 21 to 30. The residual plots from 5 different least squares regression line are shown below. Which of the plots provides the strongest evidence that the regression line is the appropriate model for the data and is consistent with the assumptions required for inferences about regression? Well, ideally, our residual plot should have absolutely no pattern to it. Clearly, there's a pattern here. Oh, let's make this happy. Okay, maybe it didn't have a smiley face, but nonetheless, A is inappropriate. We also have a pattern here. So this is not good. I'm looking at C, and you know what? It's centered on 0, as it should be, and it appears pretty random. When I look at this one, I definitely see a pattern of convergence, all right? And since I have a pattern, D is not well. Now this pattern is a result of my variation changing. And we don't want our variation to change, all right? But my variation is changing, so we have a pattern. This is not good. When I look at this one, I also see my variation changing. And so I also have a pattern. And this time I'm diverging. All right, as my x's increase, I diverge. Here my x's increase, I converge. But because my variation is changing, I have a pattern. E is not correct. My best group is this random here because I have no idea, no prediction, no pattern, and my spread is about the same. So C looks good. The variation looks good on that as well. All right, number 22. A random sample of 50 students at a large high school resulted in a 95% confidence interval for the mean number of hours of sleep per day. And this is what they came up with. So on average, we believe we're 95% confident that the true population mean sleep time is somewhere between 6.73 and 7.76 hours. This is not for any individual. This is for the average, all right? We believe the true population is somewhere between there. Could be as low as 6.3, that's plausible, or as high as 7.67 is also plausible, any value in between. Which of the following statements best summarizing the meaning of this confidence interval? This doesn't say confidence level, so we're not talking about in repeated sampling. We're saying the probability, or not the probability, how confident we are that we captured the true population mean of sleeping when we're 95% confident. About 95% of all random samples of 50 students from this population would result. No, every sample is different. We cannot say that it's going to have the same values. About 95% of all random samples of 50 students from this population would result in a 95% confidence interval that covered the population mean number of hours of sleep per day. So real quickly, I'm actually liking this one a lot because we're talking about the population mean, and we're going, you know what? We're about 95% confident that it will do this. And if we did of all intervals, 95% of the time, we're going to capture it. This is sounding pretty good. Let's continue reading. 95% of the students in the survey reported sleeping. No. We're 95% confident the mean lies in there, not how many students lie in there. 95% of the students in the high school sleep. Nope. We're only talking about the mean. Actually, no students may sleep that much. It could have something that look like this, where no students sleep there, but the mean is there, in which case the mean could be there, but no student be there. A student selected at random. Nope. So our best answer is B, because why? It says capturing the population mean number of hours of sleep. All right, and if this has been the sample number of hours, that's wrong. The sample number of hours is always in there. We want to capture the population mean number of hours, and we're 95% confident that we've done so. All right, number 23. A local company is interested in supporting an environmentally friendly initiative such as carpooling among employees. The company surveyed all of the 200 employees at the downtown office. Employees responded as to whether or not they own a car and to the location of the home where they live. The results are shown in the table below. So we own a car, either you do or you don't. live in the downtown, elsewhere in the city, or outside the city. Call these the burbs, all right? Which of the following statements about a randomly chosen person from the 200 employees is true? If the person owns a car, so given they own a car, and by the way, if means is like another word saying given. So given a car, so basically at this point, like, oh, I'm looking at car ownership, that's 60 people. All right. He or she is more likely to live elsewhere in the city than to live downtown. Well, elsewhere in the city is 15 out of 60. 15 out of 60. Downtown is only 10 out of 60. And 15 out of 60 is greater than 10 out of 60. That is a true statement. So A is the correct response. Continuing on. If the person does not own a car, so now we're looking here. So not own a car, and there's 140 of them that don't. That's like a given statement. Given they don't own the car, he or she is more likely to live outside than to live inside. Well, outside is 25, and it doesn't matter whether you use, and then here we have 60 plus 55, which is 110, 115 over 140. Well, this is false. That's definitely less, so that's false. The person is more likely to own a car if he or she lives in the city or in the city than if he lives outside. So owning a car but if they live in the city or elsewhere, they're more likely to own a car. Well, 70 out of, so we have a denominator of 140. And of those, 25 own a car. Outside the city, we have 35 over 60. So it's like, yep, now they're more, if they live outside, they're more likely to own a car because this percentage, 35 over 60, is definitely greater than 25. The person more likely to own is more likely to live in the downtown area in the city than elsewhere in the city. All right, in the downtown area, we have 70 out of 200. And elsewhere in the city, we also have 70 out of 200. Those are equal, and we were looking for more likely, so that's false. The person is more likely to own a car than not to own a car. All right, so if we randomly select, we have 60 out of 200 who own a car, and not own a car is 140 out of 200. So this is greater, so this is also false. So our only true answer was A. All right, number 24. A random sample of 432 voters revealed that 100 are in favor of a certain bond issue. So P hat equals X over N, which in this case is 100 over 432. So let's find out what P hat equals. 100 divided by 432 equals about 0.23. Now, technically it goes on, but we're just going to call it 0.23 to make it easy. A 95% confidence interval for the proportion of the population of voters who are in favor is, so what's my formula? P hat plus or minus Z star P hat Q hat over N. Well, P hat's 0.23. Well, that gets rid of these real quickly. So the next thing I have, plus or minus, we'll get to Z star in just a moment, 0.23 times 0.77 over N of 432. And I need to calculate Z star. Well, we're calculating a 95% confidence interval. So second vars, inverse norm, parenthesis, 1 minus 0.95, close parenthesis, divided by 2, mean is 0, standard deviation of 1, and I end up getting 1.96 as my Z star. So 24, the answer to 24 is D. Moving on to 25. The commuting time for a student to travel from home to college is normally distributed with a mean of 30 minutes. And a standard deviation of 5. If the student leaves at 8:25, what's the probability that they'll arrive at campus later than 9 a.m.? Well, 8:30 to 9 would be 30 minutes, so and add another 5. They want to know the probability that it takes the student 35 minutes or more. So they're looking for this area. So they want the probability that X is greater than 35, which is the probability that Z is greater than 35 minus 30 over 5. So this is going to be a norm CDF, lower bound 35, upper bound is positive infinity. The 30 is my mean, and my standard deviation is 5. So here we go. Second VARS, norm, CDF, lower bound, 35, upper bound, 99999, mean of 30, standard deviation of 5, oops, not 8, 5. And I get 0.1586. So 25 is A, okay? Moving on to 26. In 2009, a survey of internet usage found that 79% of adults age 18 years and older in the US use the internet. A broadband company believes that percentage is greater now. So the alternative is that P is greater than 0.79. That means our null hypothesis was that P equals 0.79. The company plans to construct a 98% confidence interval to estimate the current percentage and wants the margin of error to be no more than 2.5 percentage points, assuming that at least 79% of all adults use the internet. Which of the following should be used to find the sample size N? Well, we have an estimate this time. We have an estimate of 0.79. So our confidence interval is P hat plus or minus Z star P hat Q hat over N. This part represents our margin of error. They want a margin of error of no more than 2.5%, so 0.025. And we have an estimate for P hat. Excuse me, let me rewrite that. Equals 0.025. We have an estimate of P hat. Our estimate is that 79%. We know that it's at least that, and it's going to get larger. So consequently, 0.79 times 0.21. Now, we need to know what size, what our Z star is going to be. And since we are looking at calculating a 98%, second VARS, inverse norm, parenthesis 1 minus 0.98, close parenthesis, divided by 2. And we end up getting 2.33. So these are gone. Oh, we have an estimate at 0.79. And consequently, the one that equals 0.025 is this one. So D is our best answer, okay? The problem with this is they had the wrong margin of error, all right? Because they had the wrong margin of error. '27, a manufacturer claims its brand A battery lasts longer than its competitor's brand B battery. 9 batteries of each brand are tested independently. So we have 9 here and we have 9 here. And hours of battery life are shown in the table below. Immediately when I see that it's the same length, I start going, gosh, is this a matched pairs? It could be, all right? So let's keep that in mind. This could be a matched pairs. Provided the assumptions for inferences are met, which of the following tests should be conducted to determine if brand A batteries do in fact last longer than brand B? But it said brand are tested independent. So I have two independent samples. Because I have two independent samples, this is not a matched pair. All right. And because we're using the sample, standard deviations, this is going to be a T. All right. So we know it's going to be a T. So that gets rid of our Z-test. And they want to see if it lasts longer. So this tells me I have a greater than. So that means it's not going to be a two-sided. So that's gone. So now I'm back to these two. If this had been a paired test, I would need to be trying it out on something over and over again. So let's say I had toy A, toy B, and then I did a mean difference. But I have, instead of that, I have independent. As soon as I say independent, I have independent samples. This is going to make it a two sample T, not a matched pair, because a matched pair is dependent on the individual being tested. So this is independent. So this makes it two sample, right? Because one of the things is you have to have independence to run a two sample. They say it's independent, so it's independent. This is a two sample test, and because it's longer, it's a one-sided because we have a direction. All right, basically HO mu1 equals mu2 or mu A equals mu B. HA mu A is greater than mu B. Because we have a direction on the alternative, this is going to make it a one-sided test. All right, number 28. An experimenter concluded a two-tailed hypothesis test on a set of data with a p-value of 0.44. So let's go ahead and take a look at this real quickly. We have a two-tailed test, which means we had a not equal. And our p-value is 0.44, which means the area in each tail is 0.22. So this is the area in each tail. If the experimenter had conducted a one-tailed test on the same set of data, which of the following is true about the possible p-values the experimenter should have gotten? Well, obviously, well, maybe it isn't as obvious. Let's try this out. Let's just say this was the test value they got. I could have chosen the upper side, but I'm going to choose the lower side. Well, if I had a lower tail, this would be 0.22. And so we go 0.22 is a possible answer. Well, that gets rid of B and that gets rid of C. Okay. Now, on the other hand, let's take this same thing and we have the same X. We have 0.22 right here, but let's just say they did a greater than. Well, how much is this area? Well, this area right here would be 0.78 or 1 minus 0.22. So depending on the direction, it's either going to be, one tail to two tails, double the p-value. If you go from one tail to two tails, double the p-value. If you go from two tail to one tail, it depends on the direction of HA. In other words, whether it's a less than or greater than. And that means it's also going to depend on the question, but either the p-value is going to be p-value divided by 2, which is what we did here. We went 0.44 divided by 2, or 1 minus the p-value divided by 2. And let's try that out. So that would be 1 minus 0.44 divided by 2. This is going to give me 0.22. This is 1 minus 0.22, which is 0.78. So one tail to two tail, it's easy. We double the p-value. That's not what happened here. We went from two tail to one tail, so it depends on the direction, whether it's less than or greater than. And we're either going to have a p-value divided by 2 or a 1 minus a p-value divided by 2. In this case, our p-value is 0.44. So 0.44 divided by 2 is 0.22, which is what we said right here. Or 1 minus 0.44 divided by 2, which is 1 minus 0.22 or 0.78, which is also what we said here. And 28 is D. And this is a challenging problem, but one that you definitely should be able to get. So study it, please. All right, number 29. A randomized experiment was performed to determine whether two fertilizers, A and B, give different yields. A total of 33 tomato plants were grown, 16 using fertilizer A and 17 using fertilizer B. The distributions of the data did not show marked skewness. This is important. Why is it important? Because we have a sample sizes of less than 30, so we need to make sure the distributions are reasonably normal. There are no outliers. The results are shown in the table below. So we have average number of potatoes per plant. So this is X bar A, this is X bar B. Standard deviation A, standard deviation B, and then N A, N B. Now, real quickly, because we're talking about average, our null hypothesis is this: mu of A equals the mu of B, the alternative, and they were looking to see whether they gave different yields, which means not equal. So this is going to be, the alternative is mu A does not equal mu B. Now, if I'm doing this on a FRQ test, for the FRQ part of the test, I need to write my equation out. And my equation is going to be T equals X bar A minus X bar B over SA squared over NA plus SB squared over NB. All right. And then I would be plugging in those values. I plug in 19.54 here, 23.39 there, 3.68 here, 4.93 here, 16 here, 17 there. But because this is on multiple choice, I just go straight to the calculator, which is going to be stat test, 2 sample t-test. X1 is 19.54, 3.68 and 16, 23.39, 4.93 and 17. Then we have a not equal sign. We calculate, and I get a p-value of 0.016. All right, so that's going to be real important for this problem. There is no statistical evidence because the p-value is greater than 0.15. No, our p-value is 0.016. It's less than that, so that's false. There is borderline. Our p-value is 0.016. Well, does our p-value lie in this interval? And the answer is no, it doesn't lie in that interval. 0.016 is over here. There is evidence, but 0.016 is definitely less than 0.05. So this isn't true. There is evidence of statistical significance difference in the yields, and 0.01 is smaller than our p-value. That's true. 0.01, if we have in 0.016, We can definitely see 160 is greater than that. So that's true, but our p-value is definitely less than that. Our p-value lies within that interval. Our p-value equaled 0.016, and it fits between those two. All right. So the main thing we need to check is where does our p-value fit, and it lies between 0.01 and 0.05. All right. Another way of saying this is 0.010 is less than 0.016 is less than 0.050. 10 is less than 16 is less than 50, and this is what we calculated. Okay. All right, number 30. In order to plan its next advertising campaign, the Trendy Motor Vehicle Company is investigating whether the type of vehicle and the color of vehicle are related. Oh, so we're looking for a relationship. If we're looking for a relationship, we're going to be doing one of a couple things. We're either going to be doing a regression or chi-squared independence. All right, so we need to pay careful attention to see what we're doing. Each person in a random sample of size 275 selected from the company's mailing list was classified according to their car type, car or truck, and color of the vehicle he or she drove. Well, here, once I have multiple categories, then I'm looking at a chi-squared. As soon as I have multiple categories, it's no longer, it cannot be a regression. Even though relationship can be regression, but a chi-squared has to be test of independence. Which of the following procedures would be most appropriate for investigating whether there is a relationship between vehicle type and color? All right, so this is going to be a chi-squared test for independence. No other choices were even possible, and they didn't even have regression as a choice. All right, regression can show relationship, but if I have multiple categories, which I have, and I'm looking for a relationship, association, dependence, or independence, then it's going to be a chi-squared test of independence. All right, so multiple categories, and they ask for relationship, association, dependence, or independence. It's going to be a chi-squared test for independence. So 30 is E. All right, thank you.